The first step that I'm going to do is I'm going to show you, let me give you a few expressions with exponents. So here we go. Watch this. Exponents. So watch this. 3 to the second is 9. Okay, you understand that. 3 to the second power is 9. This is the exponent. This is the base. And this is really, you can call it the product. Because this is a product, believe it or not. This is 3 times 3. Okay? The product. All right. I'm going to express this in logarithmic form. So this is a exponent and now I'm going to express this in logarithmic. Form. To do that, remember this. Logarithms are, just remember this. Logarithms are powers. Logarithms are exponents. Let me write that down. Logarithms are exponents. You can say power if you want to. Logarithms are powers. Yes. Logarithms are exponents. Okay, just remember this. So if you look at this one, this is the base. That's the power. And call this a product if you want to. Base, power, and product. So between this one, the 3 and the 2 and the 9, which one is the power? That's the question. And I just said it. 2 is the power. This 2. So therefore, following this, between 2, 3, and 9, this 2 is a logarithm by this definition. This 2 is a logarithm, okay? So 2 is a logarithm. Yep, because 2 is the power. This is the base. This is a logarithm. This is the base of the logarithm. This is the product. Here I'm going to call it the argument. There you go. Always, in an exponential expression, the power is the logarithm. The base stays as the base of the logarithm, and this is the argument. Okay. Let me erase this because I need the room. Okay. So don't forget this. Logarithms are powers. Here's another one. Five squared. No, let me use a different one. Let me use different power, okay? How about 5 to the third is what? 125. All right. Between the 3, the 5, and the 125, which one is the or a logarithm? The 3. 3 is a logarithm, okay? 3 equals to a logarithm. This 5 is the base. This 125, I call it the argument. You can also call it the product. But here, when you put it in there, it becomes the argument of the logarithm. So argument 125. There you go. So we have expressed this as a logarithm. We have expressed this as a logarithm. Let's do one last time. One last time. Pi to the r equals k. There you go. Can you express this as a logarithm? Sure you can. This r is a logarithm. R equals to a logarithm. This pi is the base. And this k must be the argument. There you go. We went from exponential to logarithmic. We can go from logarithmic to exponential. Sure we can. Watch this. Log base 2 of 8 equals 3. That's a logarithmic expression. Can we go from logarithm back to exponential? Sure we can. Remember, this pi is the base. Look, it's the base here and it's the base there. So this 2 is the base. This 2 is the base. That 8 is the argument or the product. And this 3 is the power. So we're going to say 2 to the third is 8. Okay. This 2 to this power gives you this argument. Okay. Do it again. Let's do it again. Log base k of t equals h. Can you express this exponentially? Sure you can. This is the base, this is the power, and that's the argument. This base to this power gives you the argument. So k to the power of h gives you the argument t. Yep. There you go. So you can go back and forth. By the way, this is equivalent to that. Equivalent expressions. Okay? So watch this. Log to the base of the argument equals to power or exponent. Okay? Can you express this exponentially? Sure you can. this base to this exponent gives you this argument. So we can say the base to the exponent equals to argument. There you go. So we can go back and forth. Sure we can. We can go back and forth with logarithms, okay? So, and that's what they do here. Okay, they do it in the book. On page 442, they say that. Page 442, okay? It says, the common logarithm of a positive number x, denoted by log x, is defined by, okay, so here what they're saying is the log base 10, okay? Log base 10 of x. When the base is 10, good class, when the base is 10, you do not have to show it. So this equals to log base 10, you don't have to show it, of x. When the base is 10. When the base, I might as well just give it to you. When the base is e, log base e. E is a number. E is 2.71 of x. We call this the natural log. This is the natural log. This is the common log. Common log. Natural log. Okay? When the base is e, we call it the natural log. So this is log ln, or log naturel. It's a French word. Log naturel. Okay, L, log naturel is natural. Ln x. Note, you do not see the base here, but look, it is the log base e. They call it log naturel. Okay, natural log. Okay, so those are two logs that are going to be coming up over and over again. Okay, the book says this, look, the book says on page 442, the book says log base 10 of x equals to k if and only if what? Can we express this as an exponential expression? The base is 10. This base to this power gives you the argument. If and only if 10 to the k equals 2x. Okay. So they are related. Okay? Yes, they are related. Okay? All right. Okay. So, good class. I gotta erase this, okay? I need the room. I need the room. By the way, you could do the same thing with this one. you can say log ln of x equals k if and only if e to the k equals x. Yeah, because this has base e. This e to this power, remember, this is a power, gives you the argument. Okay, very good. Okay, so we're making the connection between logarithms and exponentials. Okay? In fact, we have enough to find the inverse of the following. Watch this. Watch this. Consider this, good class, consider this, watch this. Can you find the inverse? Let's find the inverse of f of x equals 2 to the x. Okay, we can graph this. We graphed it last time. If you remember, we graph this function. I'm gonna graph it for you guys again. Because the base is greater than 1, this function is increasing. Okay? Let me graph it for you guys. So here we go. This is x, and this is f of x. I should call, let me just say y. Y. This is y. Okay. And watch this. I'm going to graph this function. Let x be 0. What's 2 to the 0? 1. 2 to the 0 is 1. Let x be 1. What's 2 to the first? 2. 2 to the first is 2. Let x be 2. What's 2 to the second? 4. 2 to the second is 4. Let x be negative 1. What's 2 to the negative 1? Half. Let x be negative 2. What's 2 to the negative 2? 1/4. Okay, go back and look at my prior video, and I did this for you guys. I made a table. Okay, go back and look at it, okay? So this is f of x equals 2 to the x. And here's the graph. That's the graph. Don't forget, you see this point? This point is 0, 1. See this point? This point is negative 1, half. See this point? This point is negative 2, 1/4. This point, what about this point? This point is 1, 2. What about this point? This point is 2, 4. There we go. Okay? Remember how, oh, by the way, this function is 1-to-1. It's 1-to-1. Why? Well, it passes the horizontal line test. Okay? That's why this function is 1-to-1, because it passes the horizontal line test. Okay? So it is 1-to-1, it is invertible. You can find its inverse. Okay. Remember how to find its inverse? Let's find its inverse. Find the inverse of this. What's step number one? Step number one. What is step number one? If you go back to the last video, we said step number one, call this y. Y equals 2 to the x. Let f of x equals y. Step number two, interchange x and y. Step number two, this y becomes x, this x becomes y. That's step number two. Step number three, solve for y. Step number three, solve for y. Do you know how to solve for y? Sure you can. Remember, the only way to solve for y is using logarithms. Why? Well, because we just said earlier, we said logarithms are powers. You see this y? That's a power. This y is a power, so therefore this y is a logarithm. So this y equals a logarithm, and that's the base 2, and that's the argument x. And 4, call this f inverse. F inverse of x equals to log base 2 of x. And there we go, we found the inverse. Okay? If you want to graph the inverse, what do? Well, there's different ways. There's different ways. Let me graph this for you guys. It's the inverse of that. Remember what we did here? Step number 2, we interchange the coordinates. If you interchange the coordinates, you're finding the inverse. I'm going to do it in red. So you see this 0, 1, 1, 0. Right there. This is 1, 0. You see this 1, 2, 2, 1. Two, 1. You see this 2, 4, 4, 2. This is 4, 2. Yes, we're getting the inverse. You see this -1 half, half -1. Half -1 right there. Half -1. Okay. You see this -2 1/4? 1/4 -2. 1/4 -2. This is 1/4 -2. Okay? And so therefore, this is the inverse right here. Okay? That's the inverse. This is f inverse of x, and this is f of x. By the way, class, if you concentrate, you see this graph? This graph. F inverse is a function. F inverse is a function. You don't have to call it F inverse. I mean, it is the inverse of this, but it's a function itself. You can call it anything you want. You may call it h of x. Sure, you can call this h of x. It's a function. Okay? In any case, good class, we just found the inverse of this, which happens to be a function itself. Okay. Here's another one. Okay, maybe you can do this one yourselves. Can you find the inverse? Let's just find the inverse, okay? Find the inverse of f of x. Let me call it a different name, okay? Just to avoid confusion. Find the inverse of p of x equals to ln of x. Can you find the inverse? All you have to do is this. Okay? Watch this. Can you find the inverse of that? Just for fun, okay? Sure we can. What's the first step? Call this y. Y equals to what? ln of x. Okay? What's the next step? Interchange x and y. Those two get interchanged. X equals ln of y. Solve for y. Now, if you're going to solve for y, you better remember what this ln represents. Let me write it in parentheses. This x equals to log base e of y. Okay. Now we can solve for y. This is the base, this is the power, and thus the argument. This base goes under this power. E to the power x equals y. Yeah. Okay. Now call this what? P inverse. P inverse of x equals to what? E to the x. All right. Okay. By the way, good class. We just found something. I have to erase this, okay? I have to erase this. And I'm going to show you this. Look, I'm going to show you that if you go to your calculator, here's your calculator. Okay? And here's probably your window. Okay? And look for the key. Look for this key or this one. Okay? If this is what you have, e to the x, if that key is e to the x, okay, right up above, you're going to find ln x. But to get to ln x, you have to press either second, there must be a second key, to get there. I should have wrote it in red. Let me write it in red instead. Okay? So that means that the second key really is giving you the inverse of e to the x. The second key gives you the inverse. Same thing with the other one, look. They're inverse of each other. Look, good class. E to the x is the inverse of ln x. The same thing with the other one. If this is 10 to the x, guess what? What is its inverse? Log of x. This is for your calculator. So that means that the second key really gives you the inverse. Okay, it's the inverse function. Okay, just thought I'll show you that. All right, gotta erase this now. Okay. All right. So let me, everybody, allow me to perhaps graph a let's graph a function, okay? That's what we can do, good class. Let's graphing the following, okay? All right, graph this. Graph, for example, graph h of x equals to log base 3 of x, everybody. Can you graph that? Sure you can. Okay, this has to go, okay? This has to go. Let's graph that. You can make a table if you want to. When you make a table, make sure you pick smart values for x. Don't forget, this comes from an exponential where the base is 3. Remember this, base 3 is the base of an exponential. Don't forget that. So watch this. X and h of x. When you graph this, you have to pick smart values for x. What are smart values for x when you graph? Well, smart values for x are 3, same base, to a power. What am I talking about? I'm talking about this. Okay? Here's a smart value for x. You got to pick smart values. 3 to the 0. Yep. 3 to the first. 3 to the second. 3 to the third. 3 to the -1. 3 to the -2. 3 to the -3. These are smart values for x. In other words, let x be 27. Let x be 9. Let x be 3. These are smart values. Let x be 1. Let x be 1/3. Let x be 1/9. Let x be 1/27. These are smart values. Yeah. smart values for x. Okay? Okay? Those are smart values. Watch this. When you plug in 1, this is log base 3 of 1. 3 to what power gives you 1? 0. Hey, that's what we got there. We got 3 to the 0 is 1. How about this one? Log base 3 of 3. 3 to what power gives you 3? 1. Log base 3 of 9. These are smart values. 3 to the second power. Log base 3 of 27. 3 to the third power is 27. Okay? Log base 3 of 1/3. 3 to the negative 1 is 1/3. 3 to the negative 2 is 1/9. 3 to the negative 3 is 1/27. These are smart values. That's how we can graph this. By the way, whenever this base is greater than 1, oh, I better say that. I better say that. I better say the following. F of x equals to log base b of x is a function excuse me. It's a function where base is greater than 0 and base not equal to 1. If you go back to the definition of an exponential, this was also given. The base cannot be negative, the base cannot be 0, and the base cannot be 1. Okay? Note, when the base is greater than 1, can't be 1, gotta be greater than 0, but if the base is greater than 1, it's gonna be increasing. Look at this, increasing. Let me show you. Watch this. X is 1, y is 0. X is 3, y is 1. X is 9, y is 2. 3, 4, 5, 6, 7, 8, 9, y is 2. X is 1/3, y is negative 1. Here is negative, here's 1/3, negative 1. Okay, X is 1/9, y is negative 2. 1/9, almost 0, negative 2. X is 1/27, y is negative 3. X is 1/27, negative 3 right there. So we're getting this. Increasing because the base is greater than 1. That's why. Okay, increasing. Remember, the same thing happened with exponentials. When the base was greater than 1, f of x equals b to the x was increasing, okay? So we should say that. F of x equals log base b of x increases when base is greater than 1. Yep. Yeah, look. Let's do another one. Watch this. Okay. You got it? I'm sorry, I have to erase this, guys. Maybe I don't. Here, we're gonna do one in red. Let's graph g of x. G of x equals to log base half of x. Nice. Let's graph that. Okay. Let's make a table. Let's pick smart values for x. What is a smart value for x? This base to the 0. That's a smart value. Base to the first. Base to the second. Base to the -1. Base to the -2. These are smart values for x. What is base to the 0? Base half. Look, base. This is 1. That's a smart value. What's base half to the first? This is half. Half to the second? 1/4. These are smart values. How about half to the -1? 2. Half to the -2. Is it 4? These are smart values. If I were you, I would always try to pick smart values for x. Those are it. How did I get them? Take this base, raise it to a power, just like I took this base and I raised it to a power, and I got these values. These are smart values. That's it right there. Smart values. Why? Because look, now we can say, what is log base half of 1? This one. Hey, that's 0. What is log base half of half? Hey, that's 1. What is log base half of 1/4? Hey, that's 2. What is log base half of 2? Hey, that's -1. And this one must be -2. Okay, note the base is less than 1. It's still greater than 0. It's gotta be greater than 0. Okay, not equal to 1. I show you one where the base is greater than 1, but here the base is between 0 and 1, excluding. Okay. All right. Can we graph now? Yes, we can. Sure, we can. Let's start there. When x is 1, y is 0. When x is 1, y is 0 right there. Whoa. Okay. When x is 2, y is negative 1. X is 2, y is negative 1, right there. Okay? When x is 4, y is negative 2. 2, 3, 4, negative 2. Right there. Okay? When x is half, y is 1. X is half right in the middle, y is 1 right there. Okay? It's decreasing because the base is half. Decreasing. When x is 1/4, y is 2. X is 1/4, y is 2 right around there. And so therefore we get this. Whoa. Yeah. Nice. Guys, this is g of x, which equals to log base half of x. Note, when the base is less than 1, obviously greater than 0, decreasing. When the base is greater than 1, increasing. We better say that. We better say that, okay? So let's say f of x equals log base b of x decreases. When the base less than 1, greater than 0. Yeah. There we go. Okay. Good class. These are exponentials. Okay. Exponentials. All right. We can graph exponentials now. Sure we can. Okay. Now they go ahead and well, I think they do. Okay. I don't know if they do that later on, but I'm gonna wait for later, okay? All right. So you can take this you can take these functions and move them around, up and down, left and right. Even you can find their inverse functions. You can now, okay? So for example, watch this. Can we graph the following? Okay, this has to go, okay? This has to go. I'll take this away too. Watch this. Can we graph r of x equals to log base half of x minus 1 plus 2. Can you graph that? Sure you can. This is the red one. Yes, it is. Because the same base, half, same base, half. Okay. But it's been shifted. 1 unit to the right, 2 units up. So you see every point on the red graph shifted 1 unit right, 2 up. Okay, let's graph it. You see this point? 1 unit right, 2 up. Right there. You see this point? 1 unit right, 2 up. Right there. See this point? 1 unit right, 2 up. Right there. This point, 1 unit right, 2 up. 1 unit right, 2 up. Right there. 1 unit right, 2 up. There. Even the asymptote has been shifted. There you go. That's it right there. This is Arabics. Okay. All right. Okay. Let me give you next. Let me give you some properties of logarithms. Okay. These are properties of logarithms. All right. And here they are. Properties of logarithms. Properties of logs. Okay? The first property. One. Property number 1, given in the book, is log base A of 1 is 0. And log base A of A is 1. Okay? So what they're saying is, no matter what the argument is, no matter what the base is, if the argument is 1, for any base, the answer is always 0. The log base of base A of 1 is 0. No matter what the base is, of course, the base must always satisfy the definition that we gave earlier. Okay? Log, when the base and the argument are the same, the answer is always 1. 2. 2. Log base A of M plus log base A of N. Log base A of M plus the log base A of N equals to the log base A of M times N. We call this the product rule. Okay? Product rule. Whenever you add 2 logs with the same base, that equals to a log with that common base of the product. 3. Log base A of M minus log base A of N equals to the log base A of M divided by N. Note, the base the argument of the log that's being subtracted is in the denominator. So this is the quotient rule. Once again, the argument of the log being subtracted is in the denominator. This is the n. This n is the argument of the log being subtracted. 4. Log base a of m to the r. Whenever the argument has a power, the power can be brought down and become a coefficient. So this becomes r the log base a of m. They call this the product rule, the quotient rule. I'm sorry. Yeah, they call this the product rule. The power rule. I'm sorry. This is the power rule. This is the quotient rule. This is the product rule. And what do they call this? They call that the logarithms of 1 and a. Logarithm of 1, logarithm of a. Okay. I'm going to have to give you one more. I'm going to have to give you the change of base formula, okay? I'll give you the change of base formula right now. Okay? Here is the change of base formula. Change of base formula. It says this: the log base b of x equals to the log of whatever base you want. I'm going to say base u of x divided by the log base u of b. And the reason I use u is because this u, the same u, it's u, is what you want. Whatever you choose. As long as the base is greater than 1 and the base not equal to greater than 0, and the base not equal to 1, you're okay. There we go. So this u, this one, and this one is what you choose. Okay? All right. Well, let me give you an example of how do we use this. How is it that we use these properties? Let me show you how we use these properties. For example, they have a good one right here. Okay? We are going to take the following. We're going to expand log base b of the square root of x plus 1 divided by x minus 2 to the third power. When we say expand, that means that we're going to take this logarithm and express it with many logarithms. That's what it means to expand. I see this is a single logarithm. We are gonna make it into many logarithms. How? Using the properties. Okay? Okay, so we're gonna take a single logarithm and make it into many logarithms. All right, let's start. So log base b of the square root of x plus 1 divided by x minus 2 to the third. Okay? First step. I guess we can make this the square root. Let's make the square, well, we don't have to right now, but look, we can do this. This is the log of a quotient. Numerator, denominator. Numerator, denominator. Yeah. The log of a numerator divided by a denominator equals to the difference of the logs, and this denominator is in the second logarithm. Yep. By this property, by property number 3, by property number 3, this becomes the log base b of the square root of x plus 1 minus the log base b of x minus 2 to the third. See that? Okay. Now, by algebra, we can make this radical into a power. Okay. So this equals to log base b of x plus 1 to the half minus the log base b of x minus 2 to the third, and this is just algebra. Yep. You see property number 4? If I have a power, it can come down to become a coefficient. Okay? By property number 4, I can bring this half down. I can bring this 3 down. Okay? Let's do that. Power come down. Half the log base b of x plus 1 minus 3 the log base b of x minus 2. And how do we get that? How? What do we use? Property number 4. And there you go. We started with a single logarithm. We made it into 2 logarithms. The first one is being multiplied by half. The second one is being multiplied by -3. So we have expanded. That's what we say, expand. Okay? We can also make it into a single logarithm. Sure we can. We can have many logarithms, like this one, and we can make it into a single logarithm. In fact, we can do this one and make it into a single logarithm. Okay? I don't have any more room, guys. I have to erase something, right? Okay. Okay, I have to erase this now. I'm sorry. You see this one? Half log base b of x plus 1 minus 3 log base b of x minus 2. Okay, watch this. We're going to make this one into a single logarithm. We better get that. Okay? Let me erase this. Oh, doesn't matter. Okay, I'll erase it. You'll see. I'll erase it. Watch, we're gonna get this again. Okay, in fact, I'm gonna erase this and we're gonna get that. There we go. Okay, watch this. Step number 1. This can go up and this can go up by property number 4, I believe. Property number 4. By property 4, this equals to log base b of x plus 1 raised to the half minus log base b of x minus 2 raised to the third. That's property number 4. Okay. By algebra, this can become a radical. So, algebra. This becomes log base b of x plus 1, the square root of minus log base b of x minus 2 to the third. That's algebra. I just expressed this as a radical. By the quotient rule, I think that was property number 3, right? Was it property number 3? I think so. Property 3. Let me see. Just want to make sure that I quote them correctly. Yeah. By property number 3, okay, this is the quotient rule, okay? So this becomes, remember this is being subtracted, this must be the denominator. So this is log base b of, this must be the numerator, the square root of x plus 1 divided by x minus 2 to the third power, and we're back to where we started. Look, we're back there again. You see, we can go back and forth. Why do we need to do this? Well, when you solve equations, logarithmic equations, you're gonna have to go express. You're gonna have to express this in terms of many logarithms. Expand. Okay? All right. So we can go back and forth. For example, watch this. Here's a good one. Example. Consider the following. Consider this. This is log base 3 of x plus log base 3 of the square root of x plus 3 minus 1/3 the log base 3 of x minus 4. So here we have 3 logarithms. Let's make this into a single logarithm. This is important. You have to know how to do this if you're going to solve equations later. Okay? So let's make this into a single logarithm. All right. The first step I'm going to do is, you see this sum? The sum of the logs is the log of the product. So let me take the first 2. I'm going to express this as a product. Okay. So this is log base 3 of x times the square root of x plus 3 minus 1/3 the log base 3 of x minus 4. this is by, I think it's rule number 2. Property number 2. Okay? Or rule number 2. This can go up. I think that was property number 4. Yeah. By property number 4. Property number 4. This is log base 3 of x, the square root of x plus 3, and this goes up, minus the log base 3 of x minus 4 raised to the 1/3. By algebra, I'm going to express this as a radical. Okay? So this is log base 3 of x times the square root of x plus 3 minus the log base 3 of the cube root of x minus 4. See? And now, the difference of two logs is the log of the quotient, and this is being subtracted, so this is going to go in the denominator of the argument. Okay, so I think it was property number 3. Property number 3. I think it is. Okay, property number 3, the quotient rule. So this is the log base 3 of x, the square root of x plus 3 divided by the cube root of what? X minus 4. And we're done. Okay? Nice. Nice. Single logarithm. You need to know how to do that. Okay? Now, let me show you how to use the change of base formula. Okay? The change of base formula is this. Log base b of x. If you want to change the base, you can. Okay? You pick a base you want. So this is the log base u of x divided by the log base u of b. Note, this b becomes the argument. This argument stays the argument up on top. Okay. This b becomes the argument. This stays the argument up on top. And you pick the new base. This is you. This is what you pick. For example, the log base half of 1.8. Okay? Suppose you want to do the log base half of 1.8. Okay, theoretically you can pick any argument you want. Yes, you can. Okay? Theoretically. I'm sorry, you can pick any base you want. Theoretically, you can pick any base you want. But most calculators only have 2 bases. Theoretically, you can do this, look. You can say, theoretically, you can say, okay, pick a base. You pick a base. What do you want as a base? You give me a base. You want 2 as a base? Okay, fine. Watch this. Log base 2 of 1.8 divided by log base 2 of a half. You can do that. Is this convenient? No. But theoretically, this is correct. Is it convenient? No. Why? Because most calculators do not have base 2. Some do. So therefore, you want to pick one of two bases. Remember what your calculator has? Remember? I showed you earlier. Your calculator either has base 10 or base E. Okay? Your calculator. This is the window. This is a key. And here's another key next to it. And here's the second. Okay? If this is 10 to the x, and if this is e to the x, if this is 10 to the x, then this is log base 10 of x. And this is ln of x. And to get those, you better press second. Okay? And most calculators only have either log base 10 or log base e. Nothing else. So that's why this base is not convenient. It's a wrong. No, this is not wrong. This is right. Except you can't use it. You cannot find out what it is because your calculator does not have base 2 or base e. Most likely, okay? There are some calculators that do. If you do not have this base, or if you do not have base 2, no problem. You pick one of those two bases, whichever you want. Okay. Let's pick a different base then. Erase this, and pick a different base. Pick base 10. If the base is 10, you don't have to write it. Right there. Base 10, base 10. But if the base is 10, we said earlier, look, not there. You don't have to write it. Okay? Maybe I should just do this. You pick 2 first. Okay, but if you want to change the base, you can. If you want to change the base, if you want to pick base 10, you can. So this is log base 10 of 1.8 divided by log base 10 of a half. And now you can use your calculator. Now you can use this. If you want to pick this base, no problem. Pick a different base. Pick ln. So this is ln of 1.8 divided by ln of a half. And use that. And now you can approximate it. Okay, we're trying to approximate this. If you use base 2, it's correct, but it's not convenient for someone who has a calculator without this base. So therefore, pick a different base. Pick what you have. Either base 10 or base E. And now use your calculator and you get the answer. Okay? All right. Okay. That's it for today, guys. Okay? I just did section 5.5, correct? I did section 5.5. And 5.4. That's what I just did. 5.5 and 5.4. Okay, you guys can go ahead now and do the homework for 5.5, 5.4. Next, I'm gonna do section 5.6. Okay, not right now, but later on. Section 5.6. Okay, and then I'll let you know what we're gonna do after that. Okay. All right. Take care of the class. I'll see you guys soon. Bye.